Hi everybody, this is Poynting Vector and you're watching video lecture series on field theory. Come, let's go into the video. So in last class, we have seen about Poynting vector and the final equation of Poynting vector. Today we are going to see the Poynting coaxial cable. Come, let's go into the video. So here, power flow in a coaxial cable. So this is the continuation of the previous class of power flow in a coaxial cable as a Poynting vector. How it is derived. Come, let's get in. So here, consider a coaxial cable which has a DC voltage V, which have a DC voltage between the conductor and a steady state current I flows in an inner and outer conductor. The radius of an inner and outer conductor are A and B. Here we can see the coaxial cable. So over here we have a voltage V as a DC supply between the center and ground, so positive and negative. We have an radius of inner and outer. So the radius of inner sphere is A, the radius of outer sphere is B. This is what an power flow, how the resistance is calculated, how the load resistance calculated. Here, first by Ampere's law, what happens? By using an Ampere's law, what happens is the surface integral of H into dl is equal to I. That is integral of H, that is what magnetic field intensity with respect to line is equal to current. So L is the circumference of the current circular path between A and B, that is 2 pi r. Circumference of the circular path between A and B, between this is radius A, S, and what happens is um, this is radius B. So between the circumference of radius path, that is 2 pi r, here h into 2 pi r is equal to I, that is h equal to I divided by 2 pi r, that is r is a radius which is lesser than A and lesser than B. So which is lesser than A, that is lesser than A, lesser than it is r is radius between A and B. Okay, by using this Ampere's law. Here the E, what is E? E is here the E is an infinity long conductor. That is, E is an infinity long conductor. That is gamma and 2 pi epsilon r. That is, this is equation 1. Here this symbol represents the change in density. The potential difference between the conductor that is voltage. The potential difference voltage between the conductor is gamma divided by 2 pi epsilon. That is in of A comma B. That is equation number A by B. That is equation number 2. E in terms of V from the equation 1 and 2. That is E in terms of V. That is from the equation 1 and 2. Here, now we can see what is E in terms of V. That is E. We compare E equal to V divided by uh, in of B by A into R. So the power density, that is power density P equal to E into H, the power density P equal to E into H. Since E and H are always perpendicular, always perpendicular. Okay, that is E vector and H vector is always perpendicular to each other. That is P is equal to E into H, that is Poynting vector P is equal to E into H. P equal to V divided by enough A, this is equal to R, that is into I divided by 2 pi R. Now, the total power will be given by the integration of power density, the integration of power density P over any cross section area. Let's let the eliminated surface already been 2 pi R dr, 2 pi R dr. The total power for W equal to integral of V divided by in A by B, A divided by B, the radius A divided by into R radius, I into 2 pi R, that is into 2 pi R into dr, difference in radius. So power in what W equal to, we are taking the integral R is equal to A, difference in dr, we are taking this common term outside. Now 1 by R into dr. What happens here? It is the power, the total power W, sorry. the total power W, okay, the total power W is equal to V by in B by A into I into in B by A. That is nothing but total power, that is equal to V into I. The power flowing across the coaxial cable is the product of voltage and current. We know that power, the total power across the coaxial cable, the total power across the coaxial cable, the total power across the coaxial cable is equal to V into I. The voltage applied and the current flow is the total power W. This is what an Poynting vector and potential across the coaxial cable. Okay. Thank you for watching this video, and we can meet in another video. Thank you so much. Have a nice day.